Electromagnetic induction. Now this is our next lesson on electromagnetism. So we are on lesson number 4, electromagnetic induction. If you have not gone through the previous topics, I would suggest that you go through them to understand this lesson 4 on electromagnetic induction nicely. So what is electromagnetic induction? What are we going to study in this chapter? Let's start with understanding what we have learned previously. In the previous chapter on motors, we have learned that whenever there is a current carrying conductor in a magnetic field, the current carrying conductor experiences a force. Force is same as motion. Whenever there is a current carrying conductor in a magnetic field, it experiences force or motion. However, is it also possible that you have a magnetic field and you move the conductor in the magnetic field? Is it possible that this combination can create current? So that was a question that came for the first time in the mind of Sir Michael Faraday. Sir Michael Faraday is a very great scientist, and we must be thankful to him for inventing AC generators, which is a source of current for our cities, for our homes, on which the various devices run, which makes our life so comfortable. All right. So let's talk about an experiment. Move the wire in the magnetic field. It produces a deflection in the ammeter. So what are we talking about? Let us focus on this picture here. Take a wire, right? You are placing it in the magnetic field. So you have two magnets. North pole of a magnet. If it is not very clear, I'll just write it again. So this is the north pole of one magnet, the south pole of the other magnet facing each other. In between you have a region of magnetic field. In this region you have this wire. This wire is not carrying any current. It is not connected to any power supply. It is not connected to any battery. It is just connected to an ammeter. We all understand ammeter is a device which measures current. Right? You do not see any source of current here. You do not see any battery or anything. But when you move this wire in the magnetic field, what you'll notice that the needle here of the ammeter, it starts deflecting. Needle deflects. It moves away from the zero. Why? That means that there was a current produced. Right? You can carry out this test to see what difference is made, right? You can carry out this experiment in the following 4 ways. You hold the wire stationary in the magnetic field. You hold the wire stationary. You do not move the wire. What you'll see? That the ammeter reading will be stuck to 0. The ammeter will show 0 current. When there is no movement in the wire, point worth noting, when there is no movement in the wire, no current. So please do understand, you need to have magnetic field plus motion Motion is synonym to force to produce current. So when you're holding the wire stationary, as this first point says, no current. Ammeter reading will be 0. Move the magnet instead of the wire. So you do not move the wire, hold the wire stationary, instead you move the magnet. Then also you see the current. Magnetic field plus motion is happening, you will find current. Third point, move the wire faster across the magnetic field. Now you're moving the wire and you're moving faster, right? You'll see a higher current. Third point will give you higher current. You reverse the direction of the motion. If you reverse the direction of the motion of the wire, the current flows in the opposite direction. If you are, instead of moving the wire up, if you are moving the wire down, you'll see that the ammeter with needle will deflect in the opposite direction. Opposite movement creates opposite current. So let us understand these terms: EMF and the induced current. EMF and the induced current. What is EMF? The voltage produced is called the induced electromotive force. The current produced is called the induced current. Right? Let us understand these terms bit by bit. So why is there a current flowing in this wire? A current flows whenever there is a potential difference created in the circuit. If there is no potential difference created in the circuit, if there is no potential difference across the pieces of wire, the current will not flow. So if the current is flowing, which is proved by the deflection in the needle of the ammeter, if there is current flowing, there has to be a potential difference created. Now the potential difference which is created is called the EMF, electromotive force. It is called the induced EMF. Why? Because we are inducing it, we are creating it, right? And the current produced, the current which is produced in this manner is called similarly induced EMF. We are inducing this current, it is called the induced current. Alright, so how do you find the direction of the induced current? How do you find? You use the Fleming's right hand rule. So now we are talking about the Fleming's right hand rule. How does it work? The first finger again points your field, F for first, F for field. The second finger again will give you the current, and the thumb will give you the movement or the thrust, right? So let us find the direction of the flow of the current in this wire. The green arrow shows the direction of the movement of the wire. How is the field moving? The field is moving from north to south. This is your north, south. If you look at all the arrowheads, so let's apply the Fleming's right hand rule. This is your right hand. All of you take out your right hand. The first finger should point in the direction of the field, north to south. The thumb should now point in the direction of the movement of the wire. The thumb should point up, right? Then you see that your second finger gives the direction of the current. The second finger gives you your answer to the question: in which direction is the induced current flowing? So how is the induced current flowing in this particular example? It is flowing this way. So I hope it's well understood how to apply the Fleming's right hand rule. And some notes for you all to take down. Induced current can be increased by. How can you increase the induced current? Now that you have done so many exercises, you should be able to answer this question. Take a moment, you can pause this video for a moment and answer this question. Faster relative motion of the magnet and the wire will produce more current, or else you can use stronger magnet. Thirdly, you can increase the length of the wire in the magnetic field, right? The direction of the induced current can be reversed by, let's talk about the second point. How can you reverse the direction of the induced current? You move the wire in the opposite direction, or you turn the magnet around. So one of the things you'll have to do, you have to either move the wire, create motion in the opposite direction, or turn the wire around. Now here we have a worked example. Pause the video for a bit, work it out and come back. Alright, so the wire on the right, the wire that you see on the right forms a part of the circuit. When the wire is moved downwards, when the wire is moving downwards, a current is induced in it. What would be the effect of moving the wire upward through the magnetic field? So instead of moving the wire downwards, if you're moving the wire upward, what will happen to the current? If you see, use the Fleming's right hand rule. What do you figure out? The induced current will reverse. If you're holding the wire still, I'm talking about question number 2, holding the wire still in the magnetic field, if you're not moving the wire, what happens? There is no current produced. Question number 3 now. Moving the wire parallel to the magnetic field. So if you're moving the wire parallel means if you're moving this wire this way, this is called a parallel motion. So what does it mean? If you're moving the wire like this, you're not moving the wire up or down, you're moving the wire sideways. It will also not produce any current. If you want to understand why no current will be produced, please check out the supplement video to understand the technical details behind it. Check out the extra videos, the supplement videos on this topic. So right now, let us understand no current will be produced. So this was our worked example. The next topic, which develops on electromagnetic induction, is the AC generator.